Well, let's continue. We're going to look for eigen decomposition. Again, we always like to start from the easiest example. A matrix that only have no zero element on the major diagonal is called diagonal matrix. And we have already named a few special matrices. Like this I, you have 1, 1, 1 on the diagonal. This is a special diagonal matrix. We call it identity matrix. And we also learned some matrix. You have an element here, here, but all zero below the major diagonal. We call it up triangular matrix. And the other way, if you got all zeros here and above the diagonal, we call it low triangular matrix. So those are the special matrices. And if you multiply a vector, let's say the x, y, z, the result of this diagonal matrix is going to get the number 1 x, number 2 y, and the number 3 z. Basically, it's a scaling transformation. We have some exercise in the previous lesson. The simple illustration is this. You can start from a box like this size. And if I let the number 1 equal 2, number 3 equal 4, and number 2 equal 3, number 3 equal 4. And then that's 2, 3, 4. And then your x, y, z will become 2x, 3y, 4z. So the operation will extend the x 2 times to here, y 3 times to here, and then z 4 times up. You're going to get a big rectangle. So the scaling operation clearly is represented like this diagonal matrix. And also from this illustration, you can see what are the 3 eigenvectors. See, when you stretch it in this direction, this does not change. And this direction does not change, neither the vertical direction. So what changed is the magnitude. Twice here, and 3 times here, and 4 times here. So also you can realize this lambda 2, 3, 4. These 3 numbers are the eigenvalue by definition at this stage. And the 3 eigenvector is going to be this. The first unit vector along the x direction, and the second unit vector at the y direction, and the third, the unit vector at the z direction. Well, we can do the computation. It's a very easy calculation. By definition, the characteristic equation is the lambda minus the little lambda times I equals 0. So that will be lambda 1 minus lambda, lambda 2 minus lambda, lambda 3 minus lambda equals 0. So obviously, your result is this product. And just to confirm, we got the 3 eigen values. And then you follow the same operation. You let the V equal A1, B1, C1 be the eigenvector to the lambda 1. You can get this equation. Let me just do it quickly. You're going to realize the computation will confirm what you observed. The eigenvector are the 3 unity vectors here, here, and here. So put this lambda, then lambda 1, this is 0. Let's say lambda 2 not equal lambda 1. If you have trouble, the easy way is let again the lambda 1 equal 2, lambda 2 equal 3, lambda 3 equal 4. That make it easier. So if this is 0, 3 minus 2 is 1, 4 minus 3 is 1, what you get? You get B1 equals 0, C1 equals 0. You have one choice for your A1. You know, I always like this, choose A1 equal 1. That's this. And you can do the same thing to get the second and the third by select this second eigenvalue, third eigenvalue, you can get this and this. So this is a relatively easy operation. So what's good for that? The good thing is easy to calculate. We're going to define the power matrix. Just like you have x, it's a linear function, x squared is quadratic, x cubed is cubic in your algebra. We can define this matrix A times A as A squared, A times A times A as A cubed as a power matrix. Because the computation could be much more complicated. Each product you need to multiply, if it's 3 by 3 by 3, you will do 27 multiplications, you check. Nevertheless, if I have a diagonal matrix, it's very easy. The square, if we multiply, you only square to this non-zero element on the diagonal. That's just like your algebra, right? If you want a cube 3 times, you can do it again. You just have a cube in the diagonal. You can raise it to the nth power. You just put the nth power in each of these eigen values or some diagonal element. So you cannot be easier than that when you deal with a 3 by 3 matrix. So of course, we like this property and hope we can take advantage of it.